Now that we've learned the equilibrium between carbonyl compounds and their enols, we can start to explore the chemistry of them. And the first thing that we're going to talk about is halogenation in that alpha position. So carbonyl compounds can be halogenated at the alpha carbon. And the way this occurs, obviously, since we've been talking about enols, is that it occurs through the enol. And it occurs through that pi bond, just like we saw with alkenes. When alkenes get halogenated, enols can also get halogenated in a similar fashion. So the first thing that we're going to take a look at is the halogenation of aldehydes and of ketones. And we're going to see that first of all, halogenation can occur in both acidic and basic conditions. So we'll look at the mechanism of both of those. And then we're going to actually see the difference between the two, and we'll discover that the outcome of the conditions, be it acidic or basic, is quite different. So let's take a look at the reaction conditions in acidic conditions. The general reaction scheme is if I take an aldehyde or a ketone, so here I'm showing, some generic carbonyl where R could be some alkyl group, it could be a hydrogen, and I'm showing a methyl group attached to the on the other side of the carbonyl. So I react it with a halogen in the presence of an acid, and in this case the halogen can be iodine, bromine, or chlorine. Fluorine doesn't work. And what happens is I get halogenation at that alpha carbon, so that methyl group in this case gets halogenated. And if the R group was an alkyl group, we could get halogenation on the other side. So that's something that we have to be concerned about when we think about ketones. And I'll show you an example in just a little bit. So here's a particular example where I have a ketone. And notice on the left-hand side I have a benzene ring, so there are no alpha hydrogens on the alpha carbon from the benzene ring, and therefore I can't form an enol in that position, but I can form an enol on the position on the right, the alkyl group on the right. So if I treat this with iodine in the presence of an acid, nitric acid and acetic acid, then I'm going to get iodination at the alpha carbon, and my product looks like this. Right? So you see that iodine has added to that alpha carbon. Now, I said that, when you have ketones and the ketones have different alkyl groups, you can get halogenation at both of the alpha carbons, and this is something that we have to worry about. So if I'm taking a look at this particular ketone, I see that it has two alpha carbons, and each alpha carbon has a hydrogen, so I can form an enol with either one of these. And when it reacts with bromine in acetic acid, I can get bromination at the alpha carbon on the left. I can also get bromination at the alpha carbon on the right, and so I end up with a mixture. Generally speaking then, when we get mixture of products, we don't like to see this, and so this typically is not done in a procedure. And we'd have to find other ways of halogenating one or the other. So let's look at the mechanism of this reaction, and we'll start off with, my example with the benzene ring that I showed on the previous slide. I'm simply condensing the benzene ring to a pH, right, phenyl group. So I have a phenyl group which has no alpha hydrogens on it, so I don't have to worry about forming my enol there, but on the right hand side there I have a carbon that has an alpha hydrogen, so I can form an enol here. So the first thing that happens in acidic conditions, as we should know by now, is proton transfer to the carbonyl oxygen. And that of course results in a protonated carbonyl. And that protonated carbonyl, we have learned, increases the electrophilicity, but it also increases the acidity of the alpha hydrogens because electron density is being withdrawn from the alpha carbon. And so water can now come along and remove that hydrogen, and the electrons from that carbon-hydrogen bond swing up to form a carbon-carbon double bond, and the carbon-oxygen double bond now breaks, and those electrons move up to the oxygen, which has the positive charge, and so it's pulling those electrons up to it. So the result is now our enol, right? Notice we have the enol. And notice, again, in acidic conditions, you never form the enolate. It's always either a positively charged species or a neutral species. In this case, we have our neutral species, and of course we're generating the acid back again, the hydronium ion back again. Well, at this stage, we have now an alkene, right? And so we can react that alkene with iodine, just like we did normal alkenes. But this time, there is a resonance stabilization from the oxygen. And so I can donate a pair of electrons from the oxygen to the alkene, and now the alkene acts as a nucleophile and attacks the iodine. And of course I get iodide coming off. So the result looks like this, where I have a what looks like and it certainly is, a protonated carbonyl. I've added iodine to the carbon, now my alpha carbon, and the reason for this has to do with the stability of the carbocations. Remember, when we talk about addition reactions to alkenes, there's always this driving force to form the more stable carbocation. And in this case, that carbocation would be the carbon on the left because it can be stabilized by that oxygen. And now all we have to do is use iodide that came off, and we can deprotonate that carbonyl and generate our product. And so notice I have now monoiodinated my product. Now the important aspect here is, can this occur again and again? And for this particular example, the reaction stops, but for any example in acidic conditions, halogenation always stops at monohalogenation. And the reason for this, obviously in this example there are no more alpha hydrogens that we can remove, but even if there were, what's happening here is the iodine, or a halogen in general, is withdrawing electron density away from the carbon. And of course we know that the carbonyl is the oxygen's withdrawing electron density away from the carbon of the carbonyl, and it puts on this partial positive charge onto that alpha carbon, such that when I protonate, if I were to protonate the carbonyl oxygen, I form a structure that looks like this. So keep in mind, I now have this protonated carbonyl, and I can draw a resonance structure of that carbonyl where I move the electrons up to the oxygen, and so I create a carbocation, and that carbocation is adjacent to a partial positive charged alpha carbon due to the withdrawing of electron density from the halogen. And so what this does is it destabilizes that that intermediate, right? It destabilizes this intermediate based on that withdrawal, and therefore it's too high of an energy to actually reach that transition state, and it doesn't occur. So halogenation in acidic conditions always gives you monohalogenation, and that's important to understand. Now, in basic conditions, we're actually going to see something very different. And that is that the reaction doesn't stop at monohalogenation. And also keep in mind that in basic conditions, you're not just forming the enol, you're actually forming the enolate, right? Again, we can look at think about the mechanism of this reaction. So here I'm going to use a generic example of here I have a methyl aldehyde or a ketone, depending on what that R group is. And I'm going to treat this with hydroxide ion. And so the first step is that the hydroxide deprotonates that alpha carbon, and the electrons move up to that carbon and create our enolate. And of course, that enolate, we can show a resonance structure of that enolate where we're placing that negative charge on the oxygen. Okay, so here we now have an enolate instead of an enol. And the thing with enolates is that they are much better nucleophiles than enols. Just like alkoxides are better nucleophiles than alcohols, hydroxide is a better nucleophile than water, so too enolates are better nucleophiles than enols. And so what happens is that enolate can then react with iodine. And again, we have a pi bond here. So the pi bond attacks the iodine and is stabilized by the oxygen. A pair of electrons from the oxygen gets donated to the alkene, and now the pi bond reacts with iodine, displacing an iodide ion. And the result is monoiodination or monohalogenation in general. Again, we have that iodine that's withdrawing electron density. Now, this is important to understand because, what's happening in these particular conditions? Well, in this case, the iodine increases the acidity of the remaining alpha hydrogens, right? It's withdrawing electron density from that carbon, and so the hydrogens become more acidic, which makes it easier to form an enolate again. So multiple halogenations occur, right? So now if I draw my monoiodinated product and I still have two hydrogens on there, I'm still in basic conditions, so the hydroxide can remove another hydrogen. And I form an enolate again. And as a matter of fact, it's easier to form this enolate than the initial enolate. And so now I can, this enolate will attack iodine, displace an iodide. I form a di-substituted or dihalogenated product. And of course, I still have a hydrogen available in this case, so I can do it again, react it with hydroxide, followed by iodine, and I end up with, now in this particular case, if I have a methyl group, a triiodinated product. Pretty cool, for the most part. Now, sometimes, so in basic conditions, oftentimes we don't halogenate in basic conditions because you get multiple halogenations. And if you think about if there was an alkyl group on the left side, I could get halogenations on that left side. So essentially all of the hydrogens, alpha hydrogens, can be displaced by halogens in basic conditions. So notice in acidic conditions I get monohalogenation, but in basic conditions I get multiple halogenations. Now there's one key aspect in basic conditions, and that is when you have a methyl ketone, the reaction actually continues even further. Now, notice in my example I have a methyl ketone that I start with. And I'm forming now this Ci3. The iodines are withdrawing electron density from that carbon. And what happens is they actually stabilize the development of a carbanion in this case. So now I have a potentially good leaving group. I still have hydroxide in there. Hydroxide is a nucleophile, and the hydroxide can attack that carbonyl. Also, if we think about it, that carbonyl is very electrophilic now because All of the halogens are withdrawing electron density, plus the oxygen's withdrawing electron density, so that carbonyl carbon is very electron deficient. It's seeking electrons, and those electrons can be provided by the hydroxide. And so we get this nucleophilic addition. And it results in a tetrahedral intermediate, in which case we have a good leaving group of the Ci3. And so we reform the carbonyl and we kick off that iodomethylcarbanion. And the result looks like this. I formed a carboxylic acid, and then the carbanion, the triiodomethylcarbanion. And of course, the triiodomethylcarbanion is fairly basic, so I have an acid and a base that forms, and therefore I get this acid-base reaction to take place. And the result is that I form a carboxylate plus this is iodoform, right? So CHI3 is iodoform. If I used chlorine, I would get chloroform. If I used bromine, I would get bromoform. And so this type of reaction is called a haloform reaction because you're producing a specific type of haloform, in this case, iodoform. Now, for purposes of like qualification of certain ketones, one of the things that you can do is if you have if you think you have a methyl ketone, you can actually react it with hydroxide and iodine. And if iodoform forms, which is it's like a yellow solid, so if you get a yellow solid being produced in that reaction, then you know you have a methyl ketone. And that's one way of kind of classifying what kind of ketone you actually have. Now, we can also halogenate carboxylic acids as well. And this process is a little bit different than that of aldehydes and ketones. And the generic reaction is, here I'm taking a carboxylic acid. Notice my alpha carbon has hydrogens attached to it, because obviously if I didn't have hydrogens attached to it, then I couldn't get halogenation. And so what I'm going to do is I'm going to react this with bromine and phosphorus followed by an aqueous workup. Now there are variations to reagents. Sometimes you'll see bromine and phosphorus, sometimes you'll see bromine and phosphorus tribromide. And you know, understand that when bromine comes into contact with phosphorus, you actually generate PBr3. And we're going to see that in the mechanism in just a little bit. But the idea is that I'm reacting a carboxylic acid with bromine in the presence of phosphorus, some type of phosphorus source, followed by an aqueous workup, and what I get is an alpha brominated carboxylic acid, right? So I'm brominating the alpha carbon. This particular reaction is called the Hell-Volhard-Zelinsky, or the HVZ reaction, right? So it's called an HVZ reaction. And the mechanism is a little bit different than that of aldehydes and ketones, but there's certainly going to be some similarities. So let's take a look at how this reaction actually proceeds. The first thing that happens is the carboxylic acid reacts with PBr3. And just like thionyl chloride produces acid chlorides, reaction of carboxylic acids with PBr3 produces acid bromide. So I end up with an acid bromide here, right? And that acid bromide in acidic conditions is going to be in equilibrium with its enol form. So here's the enol form of the acid bromide. And of course, we saw with aldehydes and ketones that enols react with halogens. So too does the enol form of an acid bromide react with a halogen. In this case, we have bromine present. And so we get addition to that alpha carbon. And so the result is this. This is called an alpha bromo acid bromide, right? So we have an acid bromide that's been brominated at the alpha carbon, alpha bromo acid bromide. Now, we know that acid halides can be hydrolyzed fairly readily with water. So if I treat this in a subsequent step with water, I can generate the alpha bromo carboxylic acid, right? And that's basically how I can halogenate a carboxylic acid. So one of the things that we can also use the alpha bromo acid bromides for is to make esters and amides. We saw previously that acid halides can make esters and they can make amides, and certainly I can take an alpha bromo acid bromide and I can treat it with an alcohol and I can make an ester. So here I have an alpha bromo ester that I can produce fairly readily. So instead of using water to make a carboxylic acid, I can add an alcohol to make an ester. Likewise, instead of using water, I can take an alpha bromo acid bromide and react it with an amine or ammonia, right? So in this case, I'm using ammonia. I could use a primary amine. I could use a secondary amine, and I would get an amide that forms, right? So this is one way of making alpha halogenated esters and amides. And you can see the similarity between the reactions of carboxylic acid derivatives, excuse me, because that's exactly what it is. Now, one of the things that we have to sometimes think about as chemists is the reaction conditions. And in this particular case, I'm using bromine and phosphorus, or bromine and PBr3. And phosphorus is actually really nasty to work with, as is bromine, which we know we've used bromine. So the Hell-Volhard-Zielinski reaction is somewhat versatile, but the reaction conditions are very nauseous, they're very long, and very harsh conditions. And therefore, we typically like to see if we can modify the reactions. And there certainly is a modification to this reaction, and that modification is called the HARP modification. In the HARP modification, you're taking a carboxylic acid and you're treating it with thionyl chloride. So the idea is, in terms of the mechanism, we see that the first step is forming an acid bromide. So HARP thought, well, why instead of forming an acid bromide, don't I just form an acid chloride? So I treat a carboxylic acid with thionyl chloride and I get an acid chloride. And now I can think about brominating that alpha carbon. And if you treat this with NBS in the presence of HBr, you can actually get alpha bromination. So I end up with an alpha bromo acid chloride, which I can then treat this with water and generate my carboxylic acid. All right, so in terms of the mechanism, again, the first step that happens is I have these acidic conditions. Now, I'm not showing the formation of the acid chloride because we've already looked at the mechanism of that. So once the acid chloride forms, we treat it with NBS and HBr. In acidic conditions, we see that the carbonyl oxygen gets protonated and generates that. So here I have now my protonated carbonyl, and NBS actually acts as a base. So if you recall, the structure of NBS looks like this. And so one of the carbonyl oxygens is going to deprotonate an alpha hydrogen. And I'm going to generate my enol. So here I have my enol, and now the enol is going to react with that protonated N-bromosuccinimide. So now I have my protonated N-bromosuccinimide. I have my enol. The enol, the alkene, is going to attack that bromine, and I form this. Right. So now notice I have a carbocation. I form that protonated. This is simply protonated succinimide now. And so now I can take my carbocation, and of course that carbocation, I can show a resonance structure donating a pair of electrons from the oxygen, but I'm simply going to, and of course we know we have to deprotonate that, so I'm going to simply deprotonate this way and generate my carbonyl. So here I have an alpha bromo acid chloride, which then I'm not going to show the mechanism of that because you should know that by now. Treating with water, I get the carboxylic acid. Right. Now, what's the importance of brominating or halogenating carboxylic acids? Well, there actually happens to be a very useful synthetic utility in this type of reaction. And that is that we can take these alpha halo acids, so alpha bromo carboxylic acid, alpha chloro carboxylic acid, and we can do substitution reactions on them. And if we use ammonia, we can make alpha amino carboxylic acids, or which we typically call simply amino acids. So if I take here I take my alpha bromo carboxylic acid. I simply treat it with ammonia in excess, followed by an aqueous acidic workup. I can generate an alpha amino carboxylic acid. And this is a simple substitution reaction, right? We've seen substitution reactions of alkyl halides with amines before. This is a typical substitution reaction. So as an example, I can use this particular alpha bromo carboxylic acid, treat it with ammonia, followed by an aqueous acidic workup, and I generate this structure right here. And this structure is valine. So this is one of our essential amino acids. And this is certainly a way that organic chemists know how to make now not only essential carboxyl amino acids, but we can also start to make other types of amino acids. So that is halogenation of carboxylic acids, and you see a useful tool in making amino acids. The last part of this section deals with halogenation of esters. So we saw halogenation of aldehydes and ketones, halogenation of carboxylic acids, and now halogenation of esters. And interestingly enough, esters are not easily halogenated. And the reason, again, for this has a lot to do with the stability of the carboxylic acid derivatives. The more stable you get, the less reactive it becomes. So we're going to see amides don't undergo halogenation, and the reason for that has to do with their stability. Esters, you can halogenate them. There aren't very many examples, and it happens that all of the examples of halogenation of esters involve treatment of the ester with some type of strong, bulky base like LDA. So the first thing that happens is I take my ester, I treat it with LDA. So LDA is not nucleophilic, but it is a strong base, as we know. And so we can generate the enolate of our ester. And of course, this enolate, as in all enolates, has a resonance structure, placing the negative charge on the oxygen and generating again that that alkene pi bond. So if I treat that enolate now with bromine, I can get addition of the bromine to that alpha carbon, reforming the carbonyl, and I get alpha bromination of my ester. And so this is typically the way it works, and so we'll see this from time to time. So now we see the very first reaction of carboxylic acid derivatives and aldehydes and ketones that doesn't involve that leaving group. It actually involves the alpha carbon. Halogenation of aldehydes, ketones, esters, and carboxylic acids.